Okay guys, so here we're going to look at 3 different connected object situations and analyze each. And what I want you to be thinking about as we work through is, what do they all have in common? Okay, so the first one is kind of like the Newton's second law lab. We have an object on a flat surface, like a table, and there's a string tied to it, there's a pulley, and then the other object is hanging vertically, and we release the system. All right, so first thing we want to do is draw a free body diagram of forces on each object separately. So I want to look at this object as having gravity pulling down on it, and since it's M2, I'll call its weight N2G, and there's a tension force from the rope in this direction. Now, on the first object, we have the tension that's pulling it this way. We have the normal force from the table. We have the weight of the object, and we have friction, like this. Okay. Now, a couple of important notes as we look at this. These 2 objects are connected. So you need to understand that however rapidly M2 falls downwards, M1 has to move to the right with the same value of acceleration. Obviously, it's not the same direction, but it's the same amount of acceleration. The other important point is that because of Newton's third law, if we are thinking about like a pulley with no mass, if we ignore the effects of the pulley, which we will for now, then the tension in the rope pulling on M2 and the tension in the rope pulling on M1 have to be the same. Because you can think of it as M2 pulls on M1 by way of the rope, and M1 pulls on M2 by way of the rope. So the tension forces are the same. All right, so with those assumptions, we're going to write Newton's second law out for each object. But before we do, one last point. Whenever you have connected object problems, one of the things that's going to help us is to ask yourself which direction the objects are actually going to move. So in this case, the system is going to move in this direction. So like M1 is going to move to the right, and M2 is going to fall. So the system moves in this direction. That's going to be helpful later on. So I'm going to write out Newton's second law for the x direction for the first object. Now, since it moves to the right, I'm going to call T positive and friction negative. So I get M1 AX equals T minus friction. Okay, now I could write a y equation for object 1, but I think at this stage, if you're working on a problem like this, you probably understand by now that the normal force and the weight on object 1 are equal because it's not accelerating up or down, and there's no other vertical forces at play. So I'm not going to write that. Now, for the other object, I'm going to write M2 AY equals the net force in the y direction. Now here's where it gets a little funny, but it's going to make the math easier later. Because I know the block's going to move downwards, I'm going to call down positive for this object. So I'm going to call M2G positive and T negative. So I'm going to write it like this. So the 2 equations that describe this system are M1A equals T minus FF. Okay, so the key point here is we have 2 equations with 2 unknowns. The A is unknown, the acceleration of the system, and the tension is unknown. But we said earlier, it's the same value of acceleration and it's the same tension. So what I'm going to do to solve the system of 2 equations, I'm actually going to add the equations together. So what I'm going to do is, I'll rewrite it, but I'm going to have M1A, and I'm not going to write the x anymore, because I'm just really interested in the value of the acceleration. And then right underneath, I'm going to write M2A and the equation for that, which was M2G minus tension. The reason I did it this way is because now, when I add the 2 equations, the tension's going to cancel out. I have a positive and a negative. I'm going to get A times, well, let me write it this way, M1A plus M2A equals M2G minus friction. We can factor out an A on the left. And then solve for A. And we get M2G minus the friction force over the total mass of the system. Now, I'll go through a quick analysis of this. If you think about it, it says that the acceleration depends on how heavy the hanging weight is, which makes sense. The heavier it is, the more it's going to accelerate, and that's what the expression says. It also says that more friction would give us less acceleration. Also makes sense. In the denominator is the total mass of the system, because the more mass the system has, the more inertia it has, which is going to decrease the acceleration. So that makes sense. Now, if we also needed to know the tension, I'm not going to go through all the algebra, but basically what you would do is take your acceleration and plug it back into one of those two lines above, and then solve for t. And it doesn't matter which one you pick. Okay, let's move on to the next one. So the vertical hanging objects. This is called an Atwood's machine. If you think about the forces on the system, this has its own weight, M1G, there's a cord, so there's a tension. Same thing here, M2G and tension. Now for now, let's make the assumption that mass 1 is greater than mass 2. Now it doesn't have to be that way, but let's make that assumption for now. So if that's the case, the system's going to move in this direction. So when I set this up, for my first object, since it moves in the downward direction, I'm going to call M1G positive, and I'm going to call T negative. When I do the second object, it moves upwards. So I'm going to call T positive, and I'm going to call M2G negative. Just like above, I'm going to add the two equations together. Tensions will cancel again. This is going to become the same as it was the last time. I get A times M1 plus M2 equals M1G minus M2G. And if I solve that for A, I get M1G minus M2G over M1 plus M2. As an exercise, you should think about why that answer's got to make physical sense. I think if you analyze it carefully, it checks out. So we got that. I actually want to box this and this as well. Now, the third one, the two objects are actually in contact physically, and it's being pushed by some force. So one of the things we got to be careful of on this one is we need to draw these two objects separated from each other. Even though I know they're touching, when I draw the diagram, I want to separate them out so I can see all the forces. Otherwise, you're going to miss something. So watch how I do this. I'm going to put M1 like this, M2 like this. Now, both of them have weight and a normal force. I'll call this N1. This has a weight and a normal force on it, N2. Okay. Now, the box on the left is being pushed, so there's an applied force on it. We'll call it F or FA, whatever. Both boxes have friction working against them. I'll call that FF1 and FF2. Okay, but look at the diagram of the right, box 2. If you look at that picture, it doesn't make sense as is, because how would the box accelerate to the right with this picture? The answer is obviously it wouldn't. So you have to think about what makes box 2 accelerate to the right. And many students would incorrectly say, well, the applied force. So they start drawing an applied force on M2. That's not correct. Box 2 is not being pushed by the person or whatever. The reason box 2 is pushed is because there's contact between box 1 and box 2. Imagine taking the two boxes and separating them like in the picture, like in my force diagram, and then pushing box 1. If they're separated, box 2 is not going to move. The only reason box 2 moves is when they're touching. So in other words, it's the contact between 1 and 2 that causes 2 to move. I'm going to give that a special label. I'm going to call that the force of object 1 acting on object 2. It looks like it says F12. It's force of 1 on 2. Okay, but think about it this way. We learned from Newton's third law that if object 1 pushes object 2 to the right, then object 2 must have to push object 1 to the left. So there's also another force on this picture, F21, the force of 2 acting on 1. That's your action and reaction. Okay, now we're ready to solve it. So for the first object, I have applied force, this F21 force, and the friction acting on object 1. For the second object, I have this F12 force to the right and the friction acting on object 2. Now, if I add these two equations, F12 and F21 have the same magnitude, it's action and reaction. This is negative and this is positive, they are going to cancel. So what I'm left with is FA minus friction 1 minus friction 2. And if I solve it for A, I get this. Now, your job as the student is to look at all three of these scenarios and see what's the connecting theme. What sort of things do these problems all have in common, and think about why that is. And when we start to see that, you'll start to be able to know what the answer is going to be before you even start the problem, and that's really when we're moving towards next level.